We've seen how forces apply to electric charges. In our previous units last semester, we saw how forces applied to objects can affect their energy and how we could use energy to solve problems. For example, how potential energy of an object rolling down a hill can be used to calculate the speed of the object at the bottom. Now that we have a way to calculate electric forces on charged objects, we can calculate an electric potential energy in order to do the same thing. So let's do a quick review. Of how to use potential energy in a gravitational situation where we're pretty familiar how it works. So you throw a rock straight up, starts down here, goes up here. You have two friends. One is at 4.2 meters. Your next friend is at 6.5 meters. The 4.2 meter friend measures 7.2 meters per second, and we want to know how fast the rock is going when it goes past the next friend, right? So we can use the conservation of energy, since if there's no air resistance on the rock, then energy will be conserved, and so our final kinetic and potential energy on the rock will be equal to our initial kinetic energy and potential on the rock. And we're interested in finding the final speed, so that's associated with the final kinetic energy, minus UF. So we can plug in our equations for everything, VF squared. Now, depending on where we put our reference for the ground, uh, we could have different potential energies for the gravitation. Let's put our reference for the gravitational potential energy at the ground, just for our own purposes. So this would be 1/2 mvi squared, and then we have mgyi minus mgyf. You can see that the masses cancel out in every one of these terms, and so Vf squared is going to be equal to 2Vi, sorry, 2 canceled out, plus 2Gy minus Yf. We can take the square root of both sides and then plug in our numbers. I'll let you write the value with numbers on your own. So we have 72 points squared plus 2 times 9.8 times, remember the higher one is larger number than the lower one, so we have 4.2 minus our 6.5, and then we take the square root of all of that, and we get that it's only going at 2.6 meters per second at the higher point. We can also calculate the work done on a physical object. Work is done by a force being applied over a distance. So if you're walking down the street and there's a strong force blowing against you, in this case 27 newtons, how much work do you have to do to push against the wind if you're moving 500 meters? Well, work is the force times the distance times the angle between the two. This is not a very well posed question. So I'm going to slightly rephrase it. I'm going to say, how much work is the wind doing against you as you walk down? If you don't know why I'm rephrasing it, it's a little complicated to get into right here. So it doesn't matter too much when we're just plugging some things in here. There's a small technical reason why I'm rephrasing it. So in any case, plugging in the numbers is pretty much the same. We're going to have our 27 newtons times the distance we move, and the thing we have to figure out is what is the angle between them. Well, you are moving this way, the wind is blowing against you, so you have a cosine 180 degrees. And so we're going to have a -1 from the cosine times 27 times 500. And so that's going to be negative 13,500 joules. So let's look at the electric potential energy of a system. We're going to look at a parallel plate capacitor. Now, we kind of skipped parallel plate capacitors earlier. You might have seen them in the reading. The general idea is that you put a positive charge on one side, we'll give it a capital Q for an amount of charge, and a negative charge on the opposite side, same magnitude of charge, but negative instead of positive. And because of that, there's an electric field between them going from the positive to the negative. Right? And any charge you put in the middle, if it's positive, it will go from the plus side to the negative. Right? And obviously, if it's a negative charge, it would go the opposite way. And it turns out that the magnitude of that field is something that we can easily calculate. Epsilon naught is permittivity of free space. It just tells you how well electric fields go in just the vacuum, in just free space. And A here is the surface area of the plate that you're making the capacitor out of. So it could be a circular shape or a square or just whatever shape you want. So the more charge you have, the more electric field you're going to have. And the more spread out that charge is, because you're giving it more area in order to spread out, the weaker the electric field will be. Okay, that's all we need to know about that in order to talk about this. We also, in this example, in order to talk about the energy, we need to know how far apart the plates are. So we're going to call that a distance d. Okay, so let's say that we start with the charge, and that charge is over here on the positive side. Now, how much work is done by the electric field if it starts on the positive side and moves towards the negative side? So this is the charge little q. Well, work is equal to F d cosine theta. The force is Q times E. The distance, we just call that d. And the theta, well, the force is pointing to the right, and the direction it's moving is also to the right. So that is just 1, right? So the work is just QE times D. The work done by that electric field is QE times D. So if we were to think of the electric field, instead of being the work done by something, it's being the change in a potential energy, then we could now use this to figure out that potential energy. So let's go back to how we figured this out in terms of when we did it with gravity, right? So when we picked up an object and moved it up 1 meter, right? The work done by gravity on that object, so M was 1 kilogram, right? So the work done by gravity on that object as we lifted it or however we made it move was a negative g times 1 meter times 1 kilogram. But its change in potential was positive g times 1 meter times 1 kilogram. Right? So when we thought of it as work, the sign was negative, but when we thought of it as a change in potential energy, the sign was positive. And basically the reason for that is the thermodynamic law is that delta E equals W. So if you're thinking of work as being outside the system, acting on the system, W is on the right. But if the energy is a potential inside the system, then it was on the left to begin with. So here, when you're calculating the work, you think of little q being your system, and the capacitor is causing q to move. Well, now we're going to change our perspective. We want the capacitor to be part of our system, and q is moving along that electric field, and a potential energy is going to be changing because q is moving in that direction. Well, how much is that potential energy changing? It is decreasing by the amount that this work was increasing when we calculated it as work. So delta G, or sorry, delta U, but now it's EL for electric potential energy, is negative QED for this example. So in general, we could write this as QE delta X, and there's a plus or minus right here. We could write this as a negative, and this is decreasing if Q goes with the field. Just like in gravitational potential energy, your potential energy goes down, becomes more negative, if you go with the direction that gravity wants you to go.